This video is intended for entertainment and historical purposes only. It's not meant to be an instructional tutorial or provide professional advice. The only thing better than running a steam locomotive is successfully stopping it as needed. Working brakes are an essential requirement to avoid costly and unnecessary accidents which could otherwise occur. The Davenports both have hand-actuated brakes, controlled by a long handle in the cab. The brake handle is connected to a reach rod, which then connects to the brake arm. When you pull back on the brake arm, it pivots under the locomotive's frame and pulls the brake rigging towards the wheels, which applies the brakes. The brake rigging consists of hangers and brake beams, which the brake shoes attach to and pivot on. Brake rods and equalizers connect the brake beams to the brake arm and equalize the force applied to each wheel. If you're enjoying this project so far, do me a favor and hit that subscribe button. It doesn't cost you anything, but it really helps grow the channel. Now let's get right into restoring the brake gear for engine number 1.
So today we're doing a brake rod. This is a rod that goes between the front and rear brake beams. This is toast. The corrosion has blown it apart. You can see how it was welded and now it's all split. I had to actually cut it to get it to bits. So I'm making a new one. This was obviously made aftermarket by a blacksmith with whatever he had to hand to repair it. It's always a question when you're restoring these engines that do you make it look like you repaired it or do you make it look exactly like the original? I like to make it look like the original. This original rod would have been made out of a forging and machined up in the shop. I've made this out of some blocks, bits and pieces. I have 2 pieces of flat iron and a square piece. Bolted it all together to make it rigid, and you can see that it's been welded. I use, this is mild steel and the welding is 7018. Then I put it in a mill and I start to clean it up so that it looks like it's actually made in one piece. And with this piece you can see, you can't even see the weld. The procedure I used was drilled out this 7/8 hole. It's a 7/8 pin that goes in there. I bolted them together with a 1-inch spacer and a bolt. It goes 7/8 bolt to hold the pieces in perfect alignment because of course the weld wants to pull to keep it straight and to keep what I want going on. And now it's just a matter of me putting this in the mill and machining off the welds and making it pretty like this. And this will look pretty approximately what was in there originally. The other brake rod that goes from the back is built this way. So I've laid out the centers of these brake beam parts using chalk, and if I can shade it you'll see there's center punch marks that are made in the very center. And now I'm going to put these in the 4-jaw chuck in the lathe and center those center punch marks on the tailstock and then drill and tap these holes out to 7/8 NC. So we're going to start drilling with a center drill because it's very stiff and it will center very accurately. I have to go quite slowly with these tiny pilot drills because you can actually break the ends off if you push them too hard. They're made for a much smaller machine. So this is the tap drill. It's 25/64. This drill is big enough that the swarf will clear, and so I don't have to peck with this big drill because there's lots of room for the actual swarf to come out. And I ground the drill at such an angle that you get long strips rather than tight little curly pews so that the drill will clear itself. You do this on lathes, not necessarily so much in a drill press. Individuals not familiar with these machines may wonder how you get this chuck out of this hole. This is a Morse taper. Well, all lathes on their tailstocks have a pin inside that when you back them up far enough, it comes to bear on the end of the chuck and knocks it out like that. And then you just take it out. So now we're going to tap the hole out 7/8 NC using the lathe. We've got a wrench holding the torque from the tap, and we have a center in the end of the tap to keep it supported. If it's not supported, the tap will actually break off, which is not an exciting possibility. So start the lathe, it's on dead slow with the clutch released so it won't apply too much torque. As we go in, the crescent wrench pivots on the back of its handle and so that it stays aligned, doesn't give us any issues. This old lathe is nice and slow, so bad things don't happen too fast. Trouble with modern lathes is they don't actually go slow enough. They're great at high speed with carbide tools, but when you're doing haywire operations like this, you can end up with problems. You can see there's hardly any tab. I'm holding the wrench, just the weight of the wrench is bringing the tab out. So here's the finished product. We have it threaded through here. You've got a nice surface for this nut to go onto to lock it down solid. When you're making these replica parts, you have to think ahead on what you're actually going to do, because there's a procedure you have to follow, and if you don't follow a procedure, you don't think it through, you'll end up with something that you can't finish. For example, these two pieces were drilled in the drill press and countersunk on both sides. If I'd have drilled these afterwards, I wouldn't have been able to countersink in here. You can't get at it. Plus, having a bolt through here and a spacer maintain these in position for welding, because welding does tend to pull things around. So when you're making these parts, you got to sort of think ahead, figure out what to do first and what to do last, so that you end up with a nicely completed part that's ready to go. So this one's finished. So I'm getting ready to thread the front brake rod, and to do that I've got to support the end of the shaft. I got some 7/8 material in the chuck, and we've got to put a center in it so that we can support it. I'm turning this slowly because at the other end of the machine the rod is hanging out, and of course it's not really supported. And if you try and run the machine fast, centrifugal force will force that rod to go out of alignment, and it'll wobble all over the place and can cause damage. So you have to keep your speed down while you're doing this to put a center in. This is a quick chat why I am threading the brake rod in the lathe. These are a set of dies that are for a 7/8. They come out of a rigid power threader, and what you would normally use to thread a long bolt or a rod or whatever you're doing. This is the 7/8 bolt, and these teeth fit very nicely on these and make a nice thread. However, most dies are not driven. They drive themselves. You actually offer them into the work and they start to thread onto the work and actually drive themselves along the work as they're threading. They actually go this way. So the problem is that there is slippage involved. There isn't a positive drive. The thread is driving the thread is driving the thread. And so instead of 9 threads to the inch that these are supposed to be, these would be 8 and 7/8 threads to the inch, or something somewhat less. But in most cases it doesn't matter, because the nut is almost the same width as the die. So wherever the thread is on the bolt, the nut will fit, because it doesn't care where it was, it only cares where it is now. However, we're going to be putting the bolt into here, and this is a long distance, much wider than the nut itself. And what will happen is, because of this slippage, as you offer the bolt into this, it'll start to jam, because the hole that's been threaded in this piece is done with a tap that's the whole length, and it's very accurate. It is 9 threads to the inch from here to here without any slippage. But if I threaded this in a power threader, this would be 8 and 7/8 or something less than 9, and as it screws in, it starts to tighten up. And so I have to turn this on the lathe with a single point, where the lathe is actually driving the tool, or the single point, along the shaft, and it's exactly 9 threads to the inch. So when I'm finished, it will actually screw into here all the way to the end without jamming. And so that's why we're threading in the lathe. So this is a setup for threading. I have a tool here that is shaped for the thread. A 60-degree thread is a single carbide tool. Now you know why the center's in the end of the shaft, because it has to be supported. If I didn't have this supported, it would wobble around and push away from the tool and make a lousy thread. So it has been set up in the tailstock. Tailstock is locked down, and we're going to thread. I also have the machine set up down here for 9 threads to the inch. It's on a chart that you can probably see at 9. And so this pin is in this 9 slot, and this gearing is a D and A, which drives, and the lead screw is engaged, and it goes around to drive things. So it's a simple matter now of offering the tool into the work gradually with some lubricant, and it will cut a nice 9 thread to the inch. Now, with all things human, especially me, mistakes can happen. So before I go any farther, I want to make sure that I've actually got 9 threads to the inch. So I've got my little head thread gauge out, and I'm going to look at this and compare the thread gauge to the threads, the scratches on this, to make damn sure that I've got 9 threads to the inch, which I do. So I'm going to back this up to where I was. I had my cross slide set at 100. So now I'm going to go to 110 with some lubricant, and I'm going to cut the thread. So I'm going to continue to do this until I've cut the entire thread. I don't need to bore you with the details, and then we'll go to the next step. So here we are with the finished product. There's a 3 inches of 9 threads to the inch 7/8. This is the piece that screws on there. It's a nice tight thread because it's being pulled and pushed upon quite a bit, but it screws on just fine. And there's no play. There will be a half nut on here to jam it, to keep it from moving after it's all assembled to the crank length. But for now I'm going to go and cut the thread on the other end and go from there. So this is the finished brake rod. It's the same dimensions without the corrosion. The other end is pretty tough. So the original design parameters call for a 3/4 inch. That's what this is along here. I wanted to make it adjustable, so I used a 7/8 rod and 7/8 thread, and I turned it down in the middle to 3/4. The root diameter of a 7/8 thread is roughly 3/4 of an inch. When you're working on these engines, you have to get in your head the original design thinking of what the designers thought or what they thought was strong enough. And if they felt that a 3/4 inch rod between the 2 brakes beams was sufficient, then that was it sufficient. I didn't want to come along and thread the end of a 3/4 inch rod, because that would make the diameter much less and make it weaker. So I raised the size. You can probably see there's a ramp here, so that this diameter and the root diameter is the same, and everything is just as strong as it need be. So all the time, you can't reinvent the wheel. You got to try and figure out what the original designers were thinking and how they were thinking they were going to achieve it. I'm pretty sure this is not the original intermediate brake rod. It's just too cheesily made. Some guy made it in the bush, hammered it together out of 2 pieces. You can see the weld is starting to separate. It's really separated on the other ends. I don't know what happened to the original, but this now looks like the other brake rod with the square end and the forged part, except I've made this one adjustable. I'm disassembling the the brake rigging. And I just wanted to show you something. People get the idea that somehow there are hardened high tensile pins and bolts and bushings in these steam locomotives, and really they're just made out of basic iron. And this is a pin on the primary brake lever. I'm drilling it out, and as you can see by the swarf that's coming out, it's damn near like cast iron. It's really, really poor quality steel, close to being wrought. And it wasn't hardened, it wasn't anything. It was just a piece of mild steel, about as mild as they could find it. By comparison, you can see what I've done previously, drilling in just A36 iron. And this is the kind of drill, like swarf, I get out of it. And this one, I get nothing but crumbles. These steam engines were all made out of mild steel. It should be remembered that in steam railway days, high tensile steel was considered to be a grade 5 bolt, and standard bolts were grade 3. This is the 7/8 pin, and I've drilled it out to 13/16. There's just a tiny shell left, but I didn't drill it all the way through. You can see there's a shoulder left in there because I need something to drive it out with. So now what I'm going to do is put a drift in, and because everything has been loosened and is very stiff, if I put a drill into the bottom, it actually knocks it out like that. And you end up with a piece that looks like this. You can actually see the lap weld, or this must have been a piece of wrought iron. I don't know what it was, but it certainly wasn't any high-grade steel. So the first thing I do is, using my original, or the pin that I've made, I measure this edge against this edge to position where I want to start the length of the pin. This allows me to make all the pins the same. I have the lathe on a fairly high speed, and I just machine it down to diameter, taking a 100th thou off of time on the vernier. So now it's just a matter of changing the tooling to a parting tool, putting the machine in a lower speed because the parting tool has a hard enough life anyway, and they're expensive. And I set my calipers at 5/16, and I just measure from the surface to the edge of the parting tool, and that gives me the space to part it off. These parting tools are really nice because they tend to cup the material as it comes off, and they don't pile up very badly. When I get in a little bit, I knock the edges off with file so that they're not sharp. The part is hot because it's been machined, so I drop it into a tin can rather than fishing it out of the bottom of the lathe. That's it. The pin is so hot you can actually hear it sizzling in the can. We talked before about the tang on the end from the parting tool, and there's the same thing on the original pin. This is a quick discussion about old iron. These brake beams are forged rather roughly. They're not machined, and you can see in here where there's laps, laminar inclusions. This is not really good stuff, and as it gets old, especially this type of cheap steel, it tends to harden and get brittle. You can see another forging lap here. These can break off because the metal gets tired. The old term used to be crystallized, although I'm not sure that's the correct term. But it gets hard and it gets brittle, and the brake shoes can actually break off. So what I've done, you can see the shadow here, was I heated this whole end on each brake rod red hot and let it cool in air. And that tends to relax the steel and take the brittleness out of it. I don't have to do the whole thing, it's not going to break, but these break off. So now it's been relaxed again back to its original forged condition, and it should be okay for service. So here we have the Davenport brake rigging completed. There's a force applied here, a pull through multiple levers from a lever in the cab, or an air cylinder or a steam cylinder depending on the locomotive, but it pulls on this piece, which pulls on this equalizing lever. This little piece here is designed to allow stuff to move back and forth, and it equalizes the pull on this lever to this brake beam and the other brake beam, which is up there. So imagine, if you will, you have 1,000 pounds pulling on here, pulling back. It comes to this pin and it applies 500 pounds here and 500 pounds in the bottom to the bottom rod, the rod which we've been watching get made. In turn, this piece applies 500 pounds to this brake beam, which has a brake shoe on each end, which in turn applies 250 pounds to each wheel. Now, the reason we had to make this piece adjustable, this is at the front of the engine. This is on the front driver set. The brake shoe goes against the wheel, which is here, and tries to stop the locomotive. So this can equalize back and forth depending on the wheels and where they are and the size of the brake shoe and so on. So this equalizes itself out. And this equalizes itself out. And the only thing that's left to do is to equalize the pull through this lever, this little short lever which is in between these three pins. And the purpose of making this adjustable, this piece, is because it has to balance itself out, but this lever is supposed to be in the vertical position like that. It's not supposed to be sitting cockeyed that way or this way. And so as the shoes wear, you have to change. The only place you have adjustment is in this rod, and you lengthen it or shorten it so that when the brakes are applied, this piece is in the vertical position. So we're going to put this all away now. It's all done. It's got new pins, new cotters, everything. It's the last piece to go on. It goes under all of the other stuff, under the axles, under the valve gear. So it goes on much, much later, and we'll see how it works.
Thanks for watching right to the end of the video. If you're enjoying this project, here are a couple other episodes from the series. And don't forget to subscribe, leave me a comment, and hit that bell icon so you don't miss out on future episodes.